Hello and welcome to section 6. This is a section that should sound pretty familiar to you. It's about the quadratic formula and the discriminant. So far in this chapter we have talked about solving by graphing. We have solved by factoring. We have solved by completing the square, which is what we did in section 5. And today we're going to learn to solve by quadratic formula. So at the end of this we will have 4 different techniques for solving quadratic equations. Remember that solving a quadratic equation means that we are going to find the roots or the zeros or the solutions, which are the x-intercepts if they're real numbers. If they're not, then they are complex roots or zeros. So we're going to talk about solving by the quadratic formula and then how we use something called the discriminant, which hopefully rings a bell, to figure out how many roots and what kind of roots we will have. So the new vocabulary in this section is quadratic formula, which actually isn't new, and discriminant, which also isn't new, but pay attention for those as you go through this section. So the quadratic formula, you might remember we have a song. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So that can help you remember the beautiful quadratic formula. If you look at the quadratic formula a little bit, the negative b over 2a is actually the x-coordinate of the vertex, right? So we have the vertex formula in there, and then we have plus or minus b squared, the square root of b squared minus 4ac. So when I think about a parabola, what that means is, here's the x value of my vertex, and I have plus and minus the exact same distance on both sides of the vertex to get me to the x-intercepts, because they're going to be equally spaced around the vertex. Remember that a comes from the coefficient of x squared, b comes from the coefficient of x, and c is the constant. So if I'm plugging into my quadratic formula, in this example, a is 1, b is 5, and c is 6, and it shows you here how to plug in. I have negative 5 here because this is the opposite of b. Then underneath the square root, I have b squared minus 4 times a times c all over 2 times a. So our first example here, we're going to look at an example where when we solve, we get 2 rational roots. 2 rational roots. So we're going to solve x squared minus 8x equals 33 using the quadratic formula. And we always want to start by getting it in standard form equal to 0. So we're going to subtract 33 from both sides and rewrite my quadratic equation like this. So a is 1, b is 8, and c is negative 33. Sorry, b is negative 8, and c is negative 33. So we're going to plug those values into our quadratic formula. So b is negative 8, so I have negative 8, plus or minus b squared, negative 8 squared. Notice the parentheses because I'm plugging in a negative 8. Those are super important. Minus 4 times a, which is 1. C is negative 33 all over 2 times a, so 2 times 1. And then we just simplify it. Negative 8 quantity squared is positive 64. Negative 4 times 1 times negative 33 gives me plus 132. I add those together and I get 196. The square root of 196, you should have those memorized from section 4 when I gave you that big list. The square root of that is 14, so 8 plus or minus 14 all over 2. So since it's written like this, plus or minus, I split it up into 2 different solutions, 8 plus 14 over 2, or x equals 8 minus 14 all over 2. Simplify those. 8 plus 14 is 22. 22 divided by 2 is 11. 8 minus 14 is negative 6. Negative 6 divided by 2 is negative 3. So I have 2 rational solutions, 11 and negative 3. And the reason that I get rational solutions is because this number under the square root, the 196, is a perfect square. So when the number under the square root is a perfect square, my solutions are going to be rational. All right, try this one. Okay, if you solve this correctly, you should get b, 2, and negative 15. And there's the work if you need to look at that. All right, our next example, we're going to see what happens to give us only one rational root. Remember that when my parabola only touches the x-axis once, I only have one root. So we're going to look at when that happens in the quadratic formula. So again, just like we did before, we're going to plug in negative 34 for B, 1 for A, and 289 for C. And simplify, and notice what I get underneath the square root. Underneath the square root here, I get 0. The square root of 0 is just 0, so I'm adding and subtracting 0, which is not going to change my answer. So I only have one solution, which is positive 17. And again, that happens when I have a 0 under the square root, because I'm doing 34 plus or minus 0, so I'm only going to get 34 divided by 2, which is 17. So I only have one root. And it turns out that that root is actually the x-coordinate of the vertex. If we look at the graph of this parabola, it only touches the x-axis once at x equals 17. All right, try this one. Okay, the answer here is A11. All right, this time we're going to look at what happens when our roots are irrational, so when we don't get nice perfect squares to add and subtract. So here A is 1, B is negative 6, and C is 2, so we're going to plug that into our quadratic formula. And we're going to simplify. Negative 6 squared underneath the radical here gives me 36. This is 36 minus 8, 4 times 1 times 2. 36 minus 8 is 28. So I have 6 plus or minus the square root of 28 all over 2. The square root of 28 is not a perfect square. Right? It's not a perfect square, but I can simplify it a little bit. The square root of 28 is the square root of 4 times the square root of 7, so that gives me 2 times the square root of 7. And you can see that they wrote that here. It's 6 plus 2 square root of 7 over 2, or 6 minus the 2 square root of 7 over 2. So if we wanted to leave it in exact radical form, we would leave it like this. But if I were to put it in the calculator and get an approximation, I would have to round it off. Here they rounded to the nearest tenth and they got 0.4 or 5.6. These results you can kind of see here in the graph. I'm not going through a really nice number. It's close to 1/2 and close to 5.5, but they're irrational numbers because if I took the square root of 7, I would get a repeating decimal that goes on forever. So the 0.4 and the 5.6 are approximate. The exact solutions are here before I simplify the square root because it is irrational. If you're wondering what happened to the 6 and the 2, I forgot to show you this. I can factor a 2 out of my numerator, so that'd be 2 times 3 plus 1 square root of 7 all over 2. And then that 2 divided by 2 cancels out to 1. I can do the same thing over here. 2 times 3 minus 1 square root of 7 all over 2, and my 2's would cancel out to 1. So that's how they got 3 plus square root of 7 and 3 minus square root of 7. So anyway, this still has 2 solutions. It's just that my solutions are irrational because the number under the square root was not a perfect square. Try this one. Okay, your answer here should be D, 5 plus or minus the square root of 13 all over 2. Okay, now we're going to look at one last situation with the quadratic formula, which was when I get complex roots. We're going to apply what we know about imaginary numbers here. In this case, I have x squared plus 13 equals 6x. I need to rewrite that as x squared minus 6x plus 13 equal to 0. So A is 1, B is negative 6, and C is 13. I always have to get it equal to 0 before I solve. So when I plug in here, I'll get a positive 6 out in front. Underneath the radical sign, I get a positive 36 here, minus 4 times 13, which is 52. And when I take 36 minus 52, I get negative 16 under the square root. So notice that when I have a negative number under a square root, I'm going to get an imaginary number. Over here they show you, remember the square root of negative 16 is 4i. Why? Because this is the square root of negative 1 times the square root of 16. The square root of negative 1 is I, the square root of 16 is 4. So that gives me 4i. So I have 6 plus or minus 4i all over 2. And again, they simplified here. I can factor a 2 out of my numerator. That gives me 3 plus or minus 2i all over 2, and the 2's will cancel, and I'll just have 3 plus or minus 2i. Another way you can think about that is that I can write this as 6 over 2 plus or minus 4i over 2. And then when I simplify that, 6 over 2 is 3, 4i divided by 2 is 2i, so I have 3 plus or minus 2i. So those are complex solutions, and if I were to graph, it shows me that my parabola never touches the x-axis. Remember, I get complex roots when my graph does not touch the x-axis, because it can only touch the x-axis if my roots or my zeros or my solutions are real numbers. When they're not real numbers, it floats above or below the x-axis and never touches it. We can check them by looking into our original equation and plugging in 3 plus 2i. That's the one they show us here. So when I square 3 plus 2i, I get 9 plus 12i plus 4i squared plus 13, because of this 13 here, equals 6x. I'm plugging in 3 plus 2i for x, so I get 18 plus 12i. And when I simplify both sides, I end up with 18 plus 12i equals 18 plus 12i. Remember that here, this I squared, I always replace I squared with negative 1. So I have 9 plus 13, which is 22. Then I have 12i, and this becomes negative 4. And that's how they simplify down to 18 plus 12i. All right, you guys try this one. All right, the answer to this one is A. And there's the work if you need to pause and take a look at that. Okay, last part of this section is talking about the discriminant. The discriminant of a quadratic function is b squared minus 4ac. It's the number that's underneath the square root. So the discriminant does not include the square root. The discriminant is b squared minus 4ac. So we looked at all of these different options when we just did all of those examples. I can have, based on my discriminant, 2 real rational roots, 2 real irrational roots, 1 real rational root, or 2 complex roots. And that all depends on the number b squared minus 4ac. If b squared minus 4ac is positive and a perfect square, like example 1. So if you want to go back and look, this is like example 1. Then I will have 2 real rational roots. If my discriminant is positive and it's not a perfect square, this is like example 2, then I still have 2 roots. My parabola still crosses the x-axis at 2 places, but those are irrational, meaning the number under the square root is not a perfect square. Looking at example, this is example 2, and this one is example 3. I got those backwards. Example 3 was the example where we had irrational roots. Example 2, where my parabola only touches the x-axis at one point, which is its vertex, happens when the number under the square root, the discriminant, is equal to 0. And when my discriminant is negative, like we saw in the last example, example 4, then I have 2 complex roots because I end up with imaginary numbers because I'm taking the square root of a negative number. So let's look at this example here real quick. We're going to find the value of the discriminant. Remember, the discriminant is b squared minus 4ac. And then we're not going to solve, we're just going to describe how many roots we have and what kind they are. So to do this, we identify a, b, and c. A is 1, b is 3, and c is 5. And then we just calculate b squared minus 4ac. So in this case, that gives me 9 minus 20, which is negative 11. Since my discriminant here is negative, there are 2 complex roots. That would be the 4th example that we looked at in the chart if you're looking there on your notes. Okay, let's do another one. We're going to do the same thing here. A is 1, b is negative 11, and c is 10. When we plug into b squared minus 4ac, we get 121 minus 40, which is positive 81. So we already know, okay, our discriminant is positive. That means we're going to have 2 roots. And since 81 is a perfect square, the square root of 81 is 9, my 2 roots are going to be rational. Okay, I want you guys to try this one. The answer here is A. The discriminant is 0 and there's one rational root. And last question. The answer